Hello, I'm Paul Cox, your host for the final of three special star parties where we've been learning about our local star, the Sun. And in this episode, we'll learn how solar storms pose a threat to our satellites, our power and communications infrastructure when Earth is bombarded by high energy particles released from the Sun, just as we've been seeing over the last few weeks. We're also going to be looking at how some of that solar activity is responsible for what I consider to be one of the most beautiful and ethereal sights we can witness in the night sky, the aurora. But let's jump straight in. I'd like to welcome Slooh educator and expert guest today, Keith Wozaleski. Hello, welcome, Keith.
Hi, Paul. Thank you. It's good to be
Now
here.
then, let's start by looking back. So, can you remind us of what we learned during the first two episodes of this series?
Sure. So the first time we looked at things we can see with the Slooh telescopes, we looked at features on the sun. We looked at prominences on the limb, and we learned how a prominence becomes uh, something else when we see it face on. We looked at sunspots. We looked at active regions. In episode 2, we looked at solar flares and learned about these massive explosions of heat, light, and radiation that come from the surface of the sun from these active regions. And we looked at something we can't see, these coronal mass ejections, which are explosions and projections of actual solar material, actual plasma that's cast out by the sun out into space. And here in this diagram, we see the beginning of a coronal mass ejection. It will be helped along by the solar wind and will gradually make its way to Earth. How fast, how long will it take to get to the Earth? That depends on the power of the explosion. It will pretty much move at the same speed that it leaves the surface of the sun, helped along by the solar wind. And as I mentioned last time, the coronal mass ejection doesn't just have charged particles and plasma, it also carries a magnetic field. And this diagram is showing us that when the magnetic field of the coronal mass ejection contacts the magnetic field of the Earth, we can have some problems. And that's what we're talking about today. What happens when these particles finally get here?
Exactly. Now, actually, just to recap another thing, I took a wild guess at how many tons of solar material blasted off in a coronal mass ejection. And you've done some research since, and it turns out when I was saying millions of tons, I was kind of underestimating that a bit, wasn't I?
Yeah, the estimate is an average CME will produce billions of tons of solar material.
Wow.
You know, when you look at the size of the sun on the Slooh telescopes and you look at the size of the Earth, the Earth is like the head of a pin. It's a dot.
Yeah.
So when these things explode, there is just an enormous amount of material and billions, millions, billions. These are numbers beyond our comprehension. It's difficult to
Exactly.
even imagine a billion
Exactly. But it's a huge amount of sun stuff basically coming in our direction sometimes.
coming
So
headed straight for us.
exactly. So we have seen some of the greatest solar storms for years over the last few weeks. Now, these have been occurring since before humans existed, ever since the sun and solar system formed. But we've built a world that is quite vulnerable to these events now, haven't we?
Yeah, we've seen something unprecedented, just the development of the internet over the last 30 years. We're old enough, both of us, to remember before we had the internet. And that infrastructure, was designed with solar storms in mind. I mean, scientists have been warning about these events for, 30 years, but the systems haven't really been tested in the ways that are consistent with what has happened in the past. You talk thousands of years. We know that we've had solar storms that are stronger than what we've been experiencing. And, how are the systems going to stand up to a larger event? We don't really know.
So we're going to take a look actually at some of those historic solar storms later. But right now, let's take a look at how these solar storms and events affect specific systems and technologies. And to help us out here, we've got this wonderful diagram from the European Space Agency. Where should we start with this diagram, Keith?
I think we can start right with the sun. So we see a coronal mass ejection about to separate. A lot of times, not always, preceded by a solar flare. So we'll talk about that first. A solar flare, by the time we see it, because it's mostly light, will travel at the speed of light. So that by the time you see it, you've already been hit by it. And because there is a cloud of ionized material that follows it, this is what's going to interact with the upper atmosphere. So we're thinking about things like satellites. Those are the things that are furthest out, even though we call them near Earth orbit. They're about 600 miles off the surface of the Earth. And those are the first lines of defense, things that are going to get hit. Those ionized particles are going to hit these satellites, and it can interfere with the electrical components in satellites.
So
So that's
presumably, it would be possible for satellite manufacturers to fully protect them against this kind of radiation. But there's a big problem there, isn't there?
they can now satellites, don't forget, are launched from the Earth, so they have to be folded up. And when they get to space, that's when they extend the solar panels. Now, there are satellites that can retract their solar panels. So uh, with the CME, that helps because we have some time to prepare for that. With a solar flare, you're kind of out of luck because there is no preparation. There's no warning with a solar flare.
But they could kind of armor these things up to protect them better against radiation. But mass is everything, isn't it? When you're launching a satellite, every single kilogram costs an absolute fortune to put into space, and then it costs just as much to keep those satellites up there because they all have fuel and they have to keep boosting their orbits. And that's the other thing, isn't it? With certainly the low orbit satellites, these some of this solar energy can actually expand our outer atmosphere just marginally, which does it increase the drag on some of these low Earth orbiting satellites?
Yes, it does. And in fact, it manipulates the atmosphere so that when the satellite has to reach its exit velocity to get out of the atmosphere and to enter into orbit, it can be dragged by this by this material in the atmosphere and can come crashing back down to Earth. This just happened last year, where 5 or 6 satellites were um, launched into space, and they ran into this drag because of this change in the atmosphere due to solar material, and they didn't exit the atmosphere. They came back to Earth. So yes, that can happen,
And
definitely.
and it
And the
causes a lot.
orbit can,
Oh,
I'm
sorry.
sorry, the orbits of them can also decay, as you mentioned. So that becomes an issue too. When these things happen, these satellites can start to drift back to Earth and lose their the orbit that they happen to be in. Yeah, it's a problem.
And that causes something that the satellite operators absolutely hate doing, which is burning some of their very limited fuel to boost their orbit again, which reduces the lifespan of that particular satellite. So,
Yeah, exactly right.
what are we moving on to next, Enki?
Then I think we'll take a look at the astronauts.
Yeah, the
So
poor guy hanging out there in space all on his own looks like a pretty lonely place to be. Now, there's something on that diagram that says cosmic rays. Space is a dangerous place for humans and life forms to be anyway without solar flares and solar particles, isn't it?
it is. Fortunately, we're protected from cosmic rays in outer space. The sun also has its own protected shield that we call the heliosphere. But some of these cosmic rays can get in, and rays from the sun. So yeah, it's a nasty place. This is not somewhere where you want to be exposed, where these events are happening,
So
like
how
this
much
poor guy
protection?
is.
Yeah, exactly. He's on a spacewalk. But even if he's in, let's say, the International Space Station, I think some students out there would be quite surprised to learn that the outside skin of a lot of spacecraft is actually incredibly thin metal sheets. Not much greater than, a heavy duty kitchen foil kind of thing. And that's once again to save weight, but it doesn't provide very much protection to the inhabitants, does it?
No, especially not against things like radiation. That becomes a
Mm.
serious concern when we have these events. It's not just heat and light or the CME plasma, it's radiation. The sun is a nuclear furnace. And when this radiation hits a space station, that could potentially ground the entire crew.
Mm.
Safety is a major concern for all the space agencies, and there is a limit to how much radiation you can absorb when you're in space. So
Yeah.
if you are like this poor guy person here, if you're irradiated by one of these solar flares or CME, that could be the end of your career in space.
And it's one of the very big challenges that engineers and those in the space industry have got to look ahead for when we're looking at longer journeys, sending people to Mars and beyond, when they're going to be exposed to the general cosmic rays as much as anything, but let alone, the influence of the sun.
Yeah, to me, that is the concern. It's not how long it will get there or what do you do when you get there. How are you going to protect yourself
Yeah,
from what's out there?
yeah.
Yeah.
So okay, so we've got some space stuff going on there. Are we now coming down below into our atmosphere? Are we coming
I
down that far yet?
think so, but maybe we should talk about radio signals. These are also affected by
Yes.
solar flares and airplane navigation and GPS and that kind of stuff.
Yeah.
Anything air-based is what's going to be affected by the flare, and and that's what we have. As we move further down into the atmosphere, that's when the CME becomes more important because solar flares can affect systems here on Earth, and that's where the CME comes in because we have this plasma and this charged material that is what's going to start to affect ground-based systems.
Right. So we do hear, don't we, quite frequently when there are these solar events that, shortwave radio operators start losing signal and their range reduces and stuff like that. But it's other radio frequencies as well, is it, that are affected?
Yeah, I mean, any of these waves that are out there in space in the ionosphere, that's what is affected by the flare. But a CME can also affect those too. But like I said, we do have some time to get ready for a CME, anywhere from, 15 hours to, 3 or 4 days.
3 days. Yeah.
And we do have that effect. Yeah, it can create all kinds of problems.
So talk to me then about GPS because some weird stuff goes on or can go on with the accuracy of the GPS system. And there's something after you talk about that, there's something else I'd like to talk about, which is related, which is on the bottom left of this diagram, which is
Sure.
something I had never ever considered until we started prepping for this show. But, what are the implications for our GPS systems?
The effect isn't just on your car, and there are easy ways to see this. If you go to Google Maps or whatever, you may see that the GPS is not pointing to where you live, maybe a street or two over. Not a big deal. The big deal is when we talk about industrial applications, things like oil rigs, where they are relying on GPS coordinates to help them determine where they're supposed to drill. And if the GPS is off, you're going to be drilling in the wrong spot.
Yeah.
Uh,
And people, I think I used to. I used to assume that you see a drilling rig and all it's doing is going straight down, but actually they can guide the head of those drills now, and they can kind of meander horizontally as well as, vertically down. So that's going to make a huge difference, isn't it?
Yeah, especially if you think you're heading in one spot and you're not because the equipment is telling you something other
Yeah.
than what it is that you're
Oh,
supposed to be at.
you were also telling me about automated farm equipment the other day as well, which is using and really requiring very accurate, GPS signals because it needs to be as accurate as a few feet or meters, doesn't it?
Yeah, when you get into corporate farming, we're not talking about people out spreading seed like the sower. You're talking
Mm.
about highly mechanized equipment that is following, areas that need to be planted and they have to be planted so far apart. And, the code is written in such a way so that, you go this far, you turn here, you go that far, and that's all based on GPS coordinates. So if there's a malfunction somewhere or you're getting wrong information, you could be planting in the wrong spot. You may have a different distance. You may not be turning where you're supposed to be turning. And of course, that affects the growing cycle and the growing season. Everything is based on a time frame, and a week of a
Yeah.
system being down can have an effect on the harvest. So, you have a lot of other things involved with that.
Now, I'm sure there's a lot of things on this diagram which, have been a surprise. A couple were a surprise to me, might be a surprise to some of the students and members watching. One thing that most of us, I think, are aware of is the impact of geomagnetic storms on our power grid system. So, have we got to that point that we can talk about that one, Keith?
Yes, I think we can talk about that right now. So, yeah, as I mentioned, the CME has a magnetic field. When that magnetic field interacts with the Earth's magnetic field, it can generate a current. And that current will gravitate towards anything that conducts electricity or magnetism. So it could be something as simple as a power line, but that current is going to lead in every direction that that cable goes to. So it can go back to the transformer, it can go back to the entire grid, it can go through undersea cables, and it can hit America and then wind up in Europe. Um, there are all sorts of problems that can go wrong there. And anyone who's ever experienced an electrical problem, you can see the scope of what we're talking about here. The grid, if the grid isn't properly protected or isn't maintained and isn't turned off because of the, early warning systems, you can have major, major power blackouts and all kinds of issues.
So engineers, especially in power grid systems, have been we've known about these events and the effect that it can have for a couple of hundred years now. We'll talk about the historic events later. They've been working a great deal as they can understand these better and the impact of these. They've been working on ways to mitigate the impact of these. But we've seen some conflicting information, haven't we? Even as recently over the last couple of weeks, where some people have been downplaying the potential impact on our power systems. But you were reading a scientific paper, I think, in preparation for this, and it didn't sound like we should be sitting on our laurels quite yet.
Exactly. It's very difficult to tell, as I said, because the grids have been tested up to a certain point, and there are all sorts of preventative measures that can take. They talk about load shedding, where you can basically empty all the stored energy that's in a transformer so that if it does get hit, it can store the material that's there. Um, but the thing of it is, all of those power lines, whether they're under the ocean, under the earth, or in the sky, above your street, can still conduct all of that energy. So the systems have not been tested beyond a certain point. And that really is the question, how powerful can a storm be? We're talking about the sun and the power of the sun. Um,
Yeah, it's I don't know. As you say, we still don't quite know all of the answers to that, but it is interesting that there is still this level of conflict. We're going to talk later, probably a little bit more about what can be done with that. But it is rather interesting, and that it's still being debated. And as you say, it still hasn't been tested. One thing that we've got now, which we didn't have, and I don't know if we can go back to our very first slide. One thing that we've got now that we didn't have, certainly in 1859, or some of the events that we're about to talk about, is the early warning of these coronal mass ejections. So, how is that being done, Keith? I mean, what is this? We didn't actually say it at the beginning, but what are we looking at here?
So this is a specialized tool type of telescope that we call a coronagraph. And what it shows us is a coronal mass ejection. We can see the explosion kind of in that 4 o'clock position. So we can see the material. It's important because we know the material is headed our way. It's coming, and we have time to prepare. So we can make these arrangements that we need. We can shut down the power grids. We can contact the satellite companies and have them and engineers and have them retract the solar panels if we can do that. You know, the astronauts do not want to take a spacewalk within 3 days of when we're doing this. Drillers may not want to drill. Farmers can prepare. You may not want to plant, or you better, make some type of arrangements to get ready for this type of event. And it all comes back to this, the prediction of space weather, where we look at these types of events and study them and are able to prepare as best as we are able. And of course,
Yep.
there's plenty of room for improvement.
And we're going to talk about, some of the career opportunities that some of the students out there have. You can be a space weather forecaster. Might be working on how to make these satellites more robust, or our national grid systems more robust. But before we move off that diagram, let's go back to our other ESA, the previous one, that one. Before we move off this, we've talked a lot about all of our artificial systems and stuff like that, Keith. But there are also some impacts from these on nature, us and other animals. Is that right?
There are any type of animal that uses the Earth's magnetic field
Oh, look at that.
for
Is that a
for
homing
migration.
pigeon? That looks
This
like a
is a
homing pigeon to me.
Yeah, this is our friend, kind of our mascot here. Birds, any type of migratory bird, any type of animal that uses the magnetic field for migration or moving around. Sea turtles are also affected. Whales are believed to be affected. When we have problems and interference with magnetic fields, that's going to affect their ability to get to wherever it is they need to go. And birds are just one of the animals. This is kind of a new branch of science of studying where different animals, different species are affected. We as humans are not affected. We're protected by the Earth's atmosphere from the radiation, but because they use the magnetic field, they can have some issues and some problems getting around.
Yeah, and that would be a really interesting study, wouldn't it? Between a correlation between maybe whale beaching events or migratory birds being spotted in locations where they're not normally spotted, and whether or not that correlates to any of this solar activity. But Heath, we've been talking about some of the historic solar storms that we've witnessed, major geomagnetic storms over the last 200 years, maybe longer. Can you tell us about the most famous of those? It was called the Carrington event, wasn't it?
That is the event. If you look up anything about solar storms, you're going to learn about the Carrington event. 1859 affected the power grid of its day, which was pretty much limited to the telegraph service. So, telegraphs were on the receiving end of these solar storms. Telegraph systems were shutting down. They were blowing out transformers. They were causing fires. Uh,
Oh,
Even though everything had shut down, there was still enough current in the telegraph system itself that people were able to use the telegraphs, even though nothing was working.
okay,
So it
and
was
just a reminder, the Carrington event was roughly the same size as that solar storm we saw 2 weeks ago, wasn't it?
it was. In fact, this is a
Oh,
side-by-side comparison that we have. We have Richard Carrington's drawing that he made. And this was this active region that we had been watching move across the face of the sun. It produced an X-class flare, which is the strongest magnitude of 10, and a G4 or G5 solar storm, which is the strongest of those. So this was about the size of the same Carrington event that we saw historically. It was a very, very powerful solar
okay.
storm.
So we have seen these events also in the 20th century, wasn't Montreal and Quebec affected?
Yeah, we have had some solar storms of similar size. Montreal and Quebec were blocked out for 9 to 12 hours in 1989. We had the Northeast blackout. Sometimes you'll hear it called the New York, New Jersey. This was in 2003, 2 to 4 days, depending on where you were. But it wasn't just the Northeast, also the upper Midwest and parts of Ontario got hit. And we had a very near miss in July of 2012, which the prediction is if it had hit us directly, it would have been worse than any of these. So,
Wow. Wow. Now there have been earlier events as well that we've managed to determine by other means before science and these lovely space telescopes were monitoring the sun all the time.
yes, we have the written record, and that's kind of the way we have people talking about what has happened, but we also have the natural record. So we see effects in things like tree rings. We see storm events suggested in things like sediment. So we know we have a natural record that goes back much, much further than 200 years, more like 12,000, 14,000 years. We have detected solar storms of much greater magnitude than what we've seen in the Carrington event. So
Okay, so that's an interesting one because we know of those major events, but do we know if these are as big as they can get?
when you look at the size of the sun, and we talk about billions of tons of solar material, who is to say that we've seen the largest that we have? Even with what we look at the Carrington event, 200-year record, and we talk about the 11-year, 22-year solar cycle, there's a much larger solar cycle known as the Gleisberg cycle, uh, every 80 to 100 years. And the activity that we are in now is actually at a minimum compared to what we can expect. So the last 30 years, and even this amazing storm that we watched, is actually on the mild side of things. So
Okay.
we don't know how big the storms can get coming from the sun.
And I think that's why we shouldn't be complacent in thinking that all of the work that has been done up until now on transformers, the national grid, on protecting satellites, and everything else that we've been talking about is sufficient, which is probably quite a good segue into our next topic. We've already said that we have space weather forecasters, but that there are some superb career opportunities for students who want a job in the burgeoning space industries, aren't there?
Absolutely. If, we need students who are good in science and math. So if you have an interest in some of the things we've been talking about on the solar series, if you're interested in astronomy, if you're interested in engineering, if you're interested in space weather about what happens with the sun and what the sun can do with solar storms, the sky is the limit, literally. anything that deals with satellites and event monitoring, especially early detection. We're
Yeah.
finding out that CMEs don't just come as a one; they're not a one-off. They actually come in cycles of two or three. So if you can detect these earlier, and you're part of that, it certainly helps the system along the way.
There are so many exciting opportunities in, 21st century space stuff. Frankly, when I was a kid, I thought we were going to be on the moon by now, living on the moon. But anyway, um, we can't leave our coverage of solar storms without mentioning what I believe is one of the most beautiful celestial sights that we can see with our naked eyes, the aurora. Keith, tell us about this wonder of the night sky that so many of us have been able to see for the first time during the huge geomagnetic storm that hit us recently.
Yeah, because of the strength of the storm, aurora was seen all over the world, much further south
Mm.
than we're used to seeing, or if you're in the southern hemisphere, further north than we're accustomed to seeing. Those particles that are coming from the sun interact with the Earth's magnetic field, and here we have our animation. They are deflected by the magnetic field of the Earth, but some of them do get sucked down into the poles. The magnetic field is strongest at the poles, and we could see that type of funnel. Those particles will interact with the Earth's atmosphere and cause this beautiful effect that we know as the aurora.
We've got some lovely, lovely shots of this. We've got a couple that I think are. Oh, this was the show that I did. I was on an eclipse expedition, and we stopped off in Iceland, and this was my first and only ever glimpse at the aurora, Keith. And during that show, with Will Gator, I was told by all of the old school guys who had been chasing down these aurora for 30 years or so. Paul, you're never going to see another storm like this, so don't bother going to see. But we've got some other little clips of this, haven't we? Now these were taken these from the International Space Station, I think, Keith.
Yeah, these are the ISS. So the
Wow.
aurora are not clouds. We'll look at a final diagram, but they're not clouds. They are actually in the upper atmosphere. They're really in space,
Okay,
and the ISS flies above them.
so we're seeing all of these wonderful, wonderful colors in the aurora. What makes them different colors like that?
It has to do with the composition of the atmosphere. So when these
Oh, great
particles
diagram.
yeah, when these particles interact with the gas in the atmosphere, it will cause it to glow. The particles become ionized, very much like a neon lamp. So we see mostly green and that reddish pink color. And if you look at the chart, we're greater than 60 miles above the surface of the Earth. So just to give everyone an idea, clouds are 30 or 40,000 feet. So even though these look like
Right.
clouds, they are not clouds. This is ionized gas up in the upper atmosphere of the Earth. Like I said, 60 to 150 miles above the surface of the Earth. The ISS flies at about 250 miles above, so that's why we can see it from space.
Wow. That's a great diagram to finish with. The aurora, if you do get the opportunity of seeing the aurora and the northern or southern lights with your own naked eyes, try and make sure you do. And of course, what we've been talking about over these last three series is solar activity is either at or very near its peak in this particular solar cycle. So this is a wonderful, wonderful time to spot the aurora. Now, Keith, if students and members want to learn more about the sun, we've got some Quest learning activities. Can you give us a quick rundown on what they are?
Sure. We start off with the beginner quest. We have Sun Explorer and our dynamic star. If you know absolutely nothing about the sun, this is the best place to start. You'll take some pictures using the Slooh solar telescope and you'll pop them in. There are directions that show you how to do that. It's simple and easy to do. We move from that into our radiant star. This is an intermediate level quest where we learn about nuclear fusion and how the sun creates energy and how it affects us here on Earth. And we end with our rotating star. The sun, of course, rotates on its axis every 27 days. We will track solar features across the face of the sun as the sun rotates. They're all a lot of fun, very informative.
I think our rotating star is my favorite, but then again, I love watching the dynamic nature of the solar system. That is it for this final episode. But Keith and I are going to be jumping back on. These are like a little primer series to get you all in the mood to watch some live solar activity. So We're going to jump on air at any point if there's some particular flares going off, or maybe reports of a CME, and we'll have live views from the Canary Islands Solar Telescope. Huge thanks to our expert guest on all three episodes, Keith Wozaleski. Thank you very much. And to Gretchen Bickett, our event manager and producer for these shows. What have we got coming up at Slooh? Well, in the build up to World Asteroid Day on June 30th, I'm actually going to be attending the entire weekend in Luxembourg on that. We have a series of special star parties where we're going to learn about near Earth asteroids, both the threat that they pose to Earth, but also the opportunities to mine resources on them and use them as a stepping stone to explore the solar system and beyond. Talk about the space industries. I mean, that's asteroid mining. My goodness, I'd love to be involved with that. Anyway, we'll also learn about tracking these pesky space rocks. Yet another career opportunity for students who are going to join the space workforce. But for now, that's it. Thank you very much for joining us. Clear skies, everyone.